So first of all, we are going to start from separable differential equation. So here I am writing a differential equation dy dx equal to x squared over y, and we have to solve this differential equation. This is a first order ordinary differential equation and it is of separable type. You can easily understand that this is first order with first degree. Okay, so first of all, what we can do, at first have a look on the steps of separable differential equation. Can we separate the variables? That means we have to group f of x with dx, g of y with dy. So from this differential equation we can easily separate x squared dx with y dy. That means x squared dx is in a group and y dy is another group. So once step 1 is done, that means grouping is done, then we have to integrate both sides. So you know that integration of x squared is x cubed by 3 and integration of y is y squared by 2. So here we have two indefinite integral, first one and second one. So indefinite integral always contains a constant, that means first integral will give us constant 1 and the second integral will give us constant 2. But if we transfer, that means on right side we have c2, so c2, and from left side if we bring c1 on the right side, then it will be c2 minus c1. So you can see c2 is constant, c1 is constant, c2 and c2 minus c1 will be also a constant, c. So we can write only a constant here, that is c. Remember, a first order differential equation will contain only one constant c always. Similarly, a second order differential equation will contain two constants c1, c2. Similarly, a third order differential equation will contain three constants c1, c2, c3. So this is a first order differential equation, that means we have to write only one constant c. So despite being two indefinite integral, instead of c2 and c1 we are using only one constant c. Okay, that means c2 negative c1 is becoming c. Okay, or suppose I am going to describe by another way, that integration of x squared is x cubed by 3 and it is an indefinite integral, input one constant c1. Again, integration of y is y squared by 2 and there will be another constant c2. Now what you can do, you can write x cubed by 3 equal to y squared by 2 plus c2 negative c1. So now c2 negative c1, this is another constant. So instead of writing c2 negative c1, we can write only c. So that is x cubed by 3 equal to y squared by 2 plus c. Okay, so now this is our general solution because it involves a constant c. Have a look on the format of solution. You can see we have two formats, implicit form, explicit form. So implicit means f of xy equal to 0 and explicit means y equal to f of x. So we can keep the solution in any of the formats. Okay, let's see. We can write the implicit form, that means this is our general solution So we are writing x cubed by 3 negative y squared by 2. On the right side we have just 0. So you can see now it is of f of xy, because in left side we have a combination of xy, so this is f of xy. That means this is the implicit solution, having the form f of xy equal to 0. You can keep your solution just like this, or we can also write the explicit form. Have a look here. X cubed by 3 negative c equal to y squared by 2. We can write by this way, and then x cubed by 3 negative c times 2 equal to y squared. And now, just to write the explicit form, we can write y equal to plus minus square root of 2 times x cube over 3 by minus c. So that means what we have found, it is of y equal to f of x form. That means it is in explicit form, and it is the previous one is in implicit form. So you can keep any of the format. Okay, I am again going to describe that. Just your solution will be x cubed by 3 equal to y squared by 2 plus a constant c. So that is your final solution. Okay, once you have found the antiderivative of the two integrals, that will be your final solution. But you can also keep the solution in implicit or explicit form. I hope you understand this problem. Okay? So now I am going to describe another separable differential equation. Here we have dy dx equal to x squared e to the power 3x times y squared negative y. We have to solve this differential equation. This is of first order, first degree differential equation. So at first we have to think, can we group x square e to the power 3x with dx and y square y minus y with dy? Yes, we can separate. That means I am writing dy over y squared negative y equal to x squared e to the power 3x times dx. That means grouping is done. X is on the right side, y terms is on the left side. You can see from the previous slides that once grouping is done, so f of x with dx and g of y with dy, then we have to integrate both sides. Okay, so let's integrate. I am using integral sign. So I am writing in convenient form, integration of 1 over y squared negative y dy equal to x squared e to the power 3x dx. So we have to solve these two indefinite integrals. You can see we know how we can solve integration by parts, that is UV technique, or we have a tabular technique. That means if we have a polynomial function, we can use tabular technique and u will be in differentiation column. This is how we can use tabular technique and solve the integrals. At the same time, the method of partial fraction is used to solve integral operational function. There have two classification, proper and improper. If we have proper rational, then these three types are important. We can decompose any function. So you can see we have to find the solution for y. Finally we will get y equal to f of x for these two integrals. So here we have two indefinite integrals. The first one we can say it is I1 and the second one is I2. And for these two indefinite integrals we can use a constant plus c. Okay, so I am saying this is equation 1 and we have to find both this integral I1 and I2. So let's start with I2. Here we have x square e to the power 3x dx. It is, since x square is polynomial term, we have UV form, so we can use tabular technique. Okay, or we can also use integration by parts, but tabular technique will be very helpful because it is a speedy process. So we can solve this integral by using tabular format. On the left side we have another integral that is of proper rational type. In upper part we have 0 degree polynomial and in lower part we have second degree polynomial. Okay, so this is a proper rational. So since we have a proper rational function here, we can easily use the method of partial fraction. That means type 1, type 2, type 3, any of the three types will be applied here. So let's solve. We are starting from I2. So in I2 we have integration x square e to the power 3x dx. X square is a polynomial term, so we can use the tabular technique. Now I am making the table, first column, second column and the third column. So in first column we have sine, second column is for differentiation and third column is for integration. In differentiation column we have to place x square term, and in integration column let's place e to the power 3x. So now repeated differentiation will be done and repeated integration will be done. Calculations will be continued if we get in differentiation part 0. So differentiation of x square is 2x, differentiation of is 2, differentiation of constant 2 is 0. So finally the calculation will be stopped here. Now we have to integrate e to the power 3x, and we know that the formula is e to the power integration of e to the power mx dx equal to e to the power mx over m. So here we have e to the power 3x, that means the integral will be e to the power 3x over 3. Again we have to integrate e to the power 3x. That means repeated integration is done. So e to the power 3x integration will be again e to the power 3x by 3, and before we have 1 by 3 again, so it is e to the power 3x by 9. Now we have to integrate e to the power 3x again, and before we have 1 by 9, so e to the power 3x integration will be e to the power 3x by 3, and before we have 1 by 9, so total answer will be e to the power 3x over 27. So I am going to write e to the power 3x over 27. Now don't forget to correspond x square root e to the power 3x, 2x with e to the power 3x by 9, and 2 with e to the power 3x by 27. And the sign will be plus, then minus, plus, minus. Always for any problem it will start with plus, and then you can use alternating sign, plus minus like this way. So the integral I2 can be written we have to multiply x square with e to the power 3x over 3. The second term will be 2x e to the power 3x over 9, and the third term will be 2 times e to the power 3x over 27. And now we have to think about what will be the sign before these three terms. So plus 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 plus. I'm writing plus here. Plus 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 plus. Minus plus minus minus plus minus. Plus 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 plus. So this is how we have found the solution. I am going to erase this part so that you can clearly understand. So we have found a solution for I2, that means antiderivative for I2 has been found. And now we have to solve I1. For these two integrals we are using a constant c. So let's solve I1. In I1 you can see this is a proper rational function. So here I am writing I1 equal to integration 1 over y squared negative y dy, which is a proper rational function. So now have a look on the concept of proper rational function. We can use partial fraction to decompose, and it is going with type 1 because we need to find the factors at first. If we have a proper rational function, at first we have to find the factors. We can take y as the factor, then it will be y times y minus 1 dy. So now you see y square negative y has been written in the form y times y negative 1. So which is of type 1. That means now we can use partial fraction. So using partial fraction, so 1 by y times y negative 1 equal to a over y positive b over y negative 1. How I have written this one? See, type 1, it is going with type 1. X minus a will contain a constant a and x minus b will contain a constant b. Similarly here y is taking a constant a and y minus 1 is taking another constant b. That means it is of type 1. So now the second step will be, we have to multiply the left side denominator on both sides. So we are multiplying y times y negative 1 on both sides. Let's say this is equation 2. So we are multiplying y times y negative 1 in equation 2. This is equation 1 and this is equation 2. So now the result will be, if we multiply y times y negative 1, the first term will be 1 equals a times y negative 1 plus b times just y, because y minus 1 y minus will be cancelled, we will have just y. Okay, let's say this is equation 3. Now we have to find the constants a and b. So we can input any values of y, but we can be very tricky that if we input y equal to 0, then we will get a. If we input y equal to 1, then we will get b. Okay, so we are going to do the same thing. Now I am inputting y equal to 0. So from equation 3 I can write one equal to a times 0 negative 1, that means 0 negative 1 plus b times 0, that means it will be 0. So 1 equal to negative a. So the value of a is equal to negative 1. So we have found the first constant. Let's find the second constant b by inputting y equal to 1. So from equation 3 we can write 1 equal to a times 1 negative 1, that means it is becoming 0, 1 negative 1, ignore my handwriting, and b plus b times 1. So now we can write 1 equal to 0 plus b. That means b equal to 1. So we have found the second constant. So now we can input the value of a and b in equation 2. That means we can write one by y times y negative 1 1 by y times y negative 1 equal to a is minus 1, that minus 1 by y, it's getting bold, I am writing correctly, minus 1 by y plus b is 1 over y negative 1. So see, we have decomposed this proportional function, and before this we have an integral, so that means now we have to integrate. So integration of 1 by 1 over y times y negative 1 dy equal to integration of the total part in terms of y, that is integration of minus 1 plus 1 by y negative 1. So the left side's result will be equal to the right side. Now we have to focus on the right side. That means let's find the result for the right side. So equal to using the property of integral, we can separate. That's why we have separated integration of minus 1 over y dy plus integration of 1 over y minus 1 dy. So first of all, we can pull out the constants, that is negative 1 is being pulled out, and we have integration of 1 over dy minus 1 dy. So you know that integration of 1 over y, it will be nothing but ln modulus y plus, similarly it will be ln modulus y negative 1. We can use substitution method here. I am showing how I have written natural logarithm of absolute value of y negative 1. That is, if we consider y negative 1 equal to u, so the second step of u substitution method will be differentiation. So we are going to differentiate in terms of y on both sides, that is differentiation of y negative 1 in terms of y and differentiation of u in terms of y. So differentiation of y is 1, differentiation of 1 is 0, so I have written just 1, and du dy. So here you will get dy equal to du. So this integral can be written as integration of 1 over y minus 1 dy. Instead of this one, now we can use u, that is all y will be converted to u, so dy will be converted to du. That means integration of 1 over u du. So it is ln modulus u, so that means you can write natural logarithm of absolute value of u. Get back to y minus 1 again, that means you have natural logarithm of absolute value of y negative 1. In short, ln modulus y negative 1. So this is how I have found this result. Okay, so see, we have found also I1, and I1 and I2 have been found, so we can input I1 and I2 in equation 1. This is our I1. So in equation 1 we can replace I1 and I2. That means this is the final solution for this differential equation, and that will be a general solution. It is a general solution because it involves a constant c. From equation 1 we can now write, that means we can just input I1 and I2, that will be our general solution. So I am going to write that substituting, ignore my handwriting, substituting I1 and I2 in equation 1. So what we will get? In equation 1 you have I1 equal to I2 plus c. So input I1 here, that is negative ln modulus y plus ln modulus y negative 1 equal to, what is I2? Let's see, x square to the power 3x by 3 negative 2x to the power 3x by 9 plus something. Okay, so we have to write that one here. X square e to the power 3x by 3 negative 2x e to the power 3x over 9 positive 2 e to the power 3x by 27 plus c. So this is our general solution. Where we have a constant c. We can remove this constant if we have an initial value, but for now this is our general solution. So now we are going to eliminate C. For this, there must be a given initial value. So suppose with this differential equation we have an initial value, suppose, and it is y of 0 equals 2. That means now it is becoming an initial value problem. This is a first order differential equation. With this differential equation we have an initial value, so this is now an initial value problem. Okay, it means the term that is inside the parenthesis, it is called x, and the right side constant is the value for the dependent variable y. Okay, it is the mathematical term. We can say when x equal to 0, then y equal to 2. So using this initial value we can eliminate the constant C. So now I am going to use the initial condition, that is using the initial condition y of 0 equal to 2. So let's say this is equation 4. So from here we can write when x equal to 0, that means at that time y equal to 2. So the initial value y of 0 means when x equal to y of 0 equal to 2 means when x equal to 0, then y equal to 2. It's getting bold. I am writing in thin layer. So when x equal to 0, then y equal to 2. So from equation 4 we have to input the value of y and x in this equation. Then only we will have the value for C. So I am writing ln, and the value of y will be here, it is 2, plus logarithm of 2 negative 1. Here we have y negative 1, so here 2 negative 1 equal to, since we have x square term and x square is 0, so 0 times something, that will be 0. 0 over 3, it will be also 0. Similarly here 0 times something, that will be 0, so that means we have 0 over 9. But in the third part we have 2 e to the power 3 times 0, that means e to the power 0. I am using the green color, over 27 plus the constant C. So now what we can write, negative ln 2 plus ln 2 minus 1 is ln 1 equal to 0, negative 0 plus e to the power 0 will be 1, that means you have just e to the power 0 equal to 1, so we have just 2 over 27 plus C. So negative ln modulus 2 can be written as just ln 2, and ln modulus 1, that means ln 1 is equal to, it is 0. So we have just 2 over 27 on the right side plus constant c. Now we can easily find the value of the constant. Negative ln 2, negative 2 over 27 equal to c. So this is the value of the constant. Now we can input this one in our general solution, that means in equation 4. So then it will be a particular solution of the given differential equation. So I am going to substitute c in equation 4. So we are getting negative natural logarithm of absolute value of y plus natural logarithm of absolute value of y negative 1 equal to x squared e to the power 3x over 3 negative 2x e to the power 3x by 9 plus 2 e to the power 3x over 27 plus the constant will be replaced here, that is negative ln 2, negative 2 over 27. So I am going to write this one, negative ln 2, negative 2 over 27. So this is our particular solution. A general solution will always contain a constant c, and by using initial value or boundary value we can eliminate that constant and we will get the particular solution. I hope you understand.